Hello everyone. Myself, I am Dr. K. Madhava Rao, Assistant Professor, Department of ECE, B.V. Raju Institute of Technology. So today the topic is semiconductor device and circuits. In that, we are discussing about the field effect transistor. So in this lecture, it will be covered about what is importance of FET and what is the classification of FET and the construction of JFET and its characteristics. What is the importance of FET? What is FET stands for? Field Effect Transistor. Where we are using it? So nowadays, electronics plays major role. The electronic devices, especially the gadgets, plays a crucial role in human lives. It becomes a part of human body, like mobiles and laptops or tabs. Without that, the human survival is very unimaginable. So, what it consists of? All these electronic goods consist of ICs. What it consists of? ICs, integrated chips or integrated circuits. So, these chips may be a processors, a microprocessor, or a microcontroller, what we are using in our mobiles as well as our laptops or any electronic goods. So the backbone of this IC is this transistor. Especially, we are using FETs. The field effect transistors are used in the ICs. These FETs are basically classified into two types. One is JFET and second one is MOSFET. One is JFET and second one is MOSFET, where J stands for junction field effect transistor. So this is the internal construction of junction field effect transistor, and this is the internal construction of MOSFET, how internally it looks like. And this is the symbolic representation, how we represent in the schematics. Okay, in the same fashion, the MOSFET is represented like this. The symbolic representation, which in the schematics is we are representing like this. This is N channel MOSFET, and this one is a P channel MOSFET. N channel, and this is a P channel. This arrow indicates that flow of current. This arrow indicates that current, how the current will flow in the MOSFET. Similarly, here also this arrow represents the flow of current here and here. So based on the current flow, we are indicating the arrow. Okay. So I hope you understand the difference, how to differentiate the JFET as well as MOSFET. So the JFET is classified into two types, NJFET as well as a PJFET. And similarly, the MOSFET also classified into two types. This is NMOS and PMOS, where N stands for channel, N channel and P channel, where the current flowing through. So coming to the JFET construction. In order to construct or fabricate a JFET, especially this is an example for NJFET. This is a construction of N channel JFET, or simply called as NJFET. N channel junction field effect transistor. So this is the channel what we are going to discuss about it. This is called channel. So in order to construct a N-channel JFET, we are using N-type semiconductor material, what we call as substrate. Okay, so in order to construct a N JFET, we are using N-type or N plus substrate, where we are doping with N-type material. Okay, so after getting this N-type substrate, the two ends, what I called, these two are called ends, the two ends of the substrate is acting as a drain and source. So what is a drain and source and gate? So the JFET is a three-terminal electronic device, So the terminal names are source, drain, and gate. So it is a unlike BJT, it is also a 3-terminal electronic device having 3 terminals. One is used as a input terminal, the second one used as a output terminal, and the other one is used as a common or a control terminal, which controls the flow of current or flow of electrons, you can say. So in the NJFET construction, we are taking a N plus substrate. So this N plus substrate, the two ends of this N plus substrate acting as a drain and source. Now what we are doing is, in order to form the gate terminal, we are using a process is called diffusion. What the process is called? Diffusion process, to form a P region, to form a P region in N-type material. So we formed a P region. This is a P region. This P region we are using as a N-type in this. So this is also a P region. We are forming two P regions on the N-type semiconductor materials. So it consists of holes. What are the majority carrier in the P region? It consists of holes, and this L plus region consists of electrons. What this N plus region consists of? Electrons, right? So this, by shorting these two P regions, the P type and N type, these two P regions, by make it short, then this terminal is called a gate terminal. So there we have one source terminal, one drain terminal, and one the gate terminal. By short these two gate regions. So this is about the construction of JFET. Okay, so simple, the summary of this is, we are taking, in order to form a NJFET, we are taking a N-type substrate. The two ends are acting as a source and drain. So in order to form the gate, we are forming two P regions on both sides of N plus material. Then by shorting these two, it is acting as a gate terminal. This is called gate terminal, where the source is used as an input terminal, drain is used as an output terminal, and the gate is used as a common or a control terminal. That's it. This is about the construction of NJFET. Similarly, how to construct a PJFET? Now, so it is very simple. So in order to construct a PJFET, we need to take which type of substrate? Yes, correct. It is a P-type substrate. We need to take a P plus substrate. And these two ends acting as a source, and this is acting as a drain, and the two sides we need to form the region. Which type of regions we need to form here by using diffusion? Yeah, it is nothing but N region. It is an N region we need to form by using a process called as diffusion, and there is a junction. It is a P type and this is N type. Automatically there are two junctions are formed. So the two regions, P-N junctions, will be formed. By joining these two P-N regions, this what acting as a gate terminal. Simple. So in order to form a PJFET, we need to take P-type semiconductor material. In terms to form a NJFET, we need to take a N plus substrate or N-type semiconductor material. Simple. So this is about the construction of JFET. Next one, in order to operate, how it operates? By adding a DC, so a power supply. So here having the three terminals, how many power supplies need to connect it? Here we need to use two power supplies. One is between gate and the source. One is between the gate and second one between the source. That what we call as a VGS, gate to source voltage. And the second power supply we connected at drain, in between drain and source, that what we call as a VDS. So we have got two power supplies, one is VGS and second one is VDS. Okay, now we will see how this operation will be. Okay, so I hope you understand these things. Now we are going to the operation. After connecting, after giving proper biasing or power supply, how the current will flow from source to drain, that what we call IDS, drain to source current, how the current will flow, how this MOSFET will be turned on. So coming to this operation of JFET at various gate potentials or biasing potentials. So first of all, why we need to apply a negative supply in this between the gate and source? Because so if you see this one, there is a channel between the source and drain. This is the width of the channel. This is called width of the channel. So if the width of this channel, width of channel, a channel width is more, then the current is more number of electrons will goes from source to drain. Whenever the electrons are moving from source to drain, then the current will flow from drain to source. That current what we call drain to source current. That current what we call as drain to source current. So whenever, in order to attract the electrons towards this drain terminal, in order to attract these electrons towards this drain terminal through the channel, so as electron is a negative potential, we need to apply a positive supply here, because the opposite poles are attract each other. So this positive polarity drift the electron towards the positive terminal. So then only there is a current flow. The electrons will move so that there is a current from drain to source. So what I want to say is, the drain to source voltage, whenever it is greater than 0, then only there is a current IDs. The ID is also greater than 0. If it is not possible, if VDS is less than 0, there is no current. The current is equal to 0. This region what we call as a cutoff region. This region what we call as cutoff region. Cutoff means there is no current flowing from drain to source. Right. So now we need to understand what is the role of VGS. So already there is a channel, there is inbuilt channel in the JFET. This operation is called, this mode of operation is called depletion mode operation. This mode of operation is called depletion mode, where the channel will depleted, then only the transistor will be turned off. So how to close this channel? In order to close this channel, we need to apply a negative voltage source between gate and source. We need to apply a negative voltage source, because the p-type is connected to negative, and this p-type is connected to negative, and this n-type is connected to positive. This bias what we call as a reverse biased. Whenever this PN junction is reverse biased, then the width of this region, this what we call a depletion width, they are different. Channel width is different and depletion width is different. The depletion width will increase with respect to applied voltage. This width is increases with respect to applied voltage. As the VGS increases, the width will increase. When the depletion width increases, the channel width will decrease. With increase in voltage, the depletion width increases, so the channel width decreases. Due to decrease in channel width, the IDS or ID will decrease. The drain to source current will decrease, because the less number of electrons will flow from source to drain. So very less number of electrons will flow from source to drain. So the first condition is, in order to conduct the current, in order to get the current, the VDS should be greater than 0, and the second condition is the VGS is less than 0. To turn off this one, to turn off the transistor, the VGS is less than 0. Then only the transistor goes into the cutoff region. So the conclusion of this story is, the IDS, the drain to source current, is depends on both VGS and VDS. This depends on both VDS and VGS. So this what we call as a voltage control device. Voltage control current source. Voltage control current source. The FET is called as voltage control current source because the input voltage is control the output current. The output current is controlled by input voltage. So the FET is called as voltage control current source. Right? Whenever the VGS is negative, this transistor goes to cutoff region. Whenever VGS equal to 0 and VDS is greater than 0, then only the transistor will conduct. Means the transistor is on and off. When it is on, the transistor is on whenever the condition is the VGS should not be negative, means the VGS should be 0, and the second condition is the VDS is greater than 0. This is the first condition to turn on the transistor. To turn off the transistor, one condition is VDS is equal to 0. The second one is, or we can say VGS is less than 0. When VGS negative and VDS equal to 0, the transistor is go to cutoff region where the current is equal to 0. This is on and off, how the transistor will on and how the transistor will off. So see this, when VGS is more negative, the two regions are interacting with each other, connecting with each other, so there is no channel. There is no channel to pass the electron from here to here. So that is the condition what we discussed about VGS is very less than 0. So I hope you understand this operation. Only the thing is the output current, the drain to source current is depends on two things. One is VGS and second one is VDS. When VGS is negative, the junction will be, the depletion width increases with increase in voltage. So the channel width decreases. So the IDE decreases. And whenever the VDS is less than 0, the electrons unable to flow. So IDS equal to 0. So when we will get current? The current we will get whenever the VDS is greater than 0, so that the IDS is greater than 0. The condition is the VDS should not be negative. The VGS should be 0. So this is about the operation of JFET with respect to VGS as well as VDS. So we can observe here. So I am applying only VDS here. I am off this VGS, means the VGS at this position, the VGS equal to 0 because it is an open switch. There is no connection. So only we are applying the VDS, there is a channel. So as of now, we discussed about the 2 points. The transistor is off. The transistor is in off state whenever VGS is less than 0 or VDS is equal to 0. The transistor is on whenever the VGS equal to 0 and VDS is greater than 0. So here also there are two cases, the case 1 and case 2. In the case 1, what happens when VDS is less than VP, that is called pinch off voltage, and second one is VDS is greater than VP. There are two conditions when the transistor is on. If it off, no, there is no other way. The current is simply 0. But when the transistor is on, the current acting is differently at different condition. One is VDS is less than VP and VDS is greater than VP, where VP is a particular voltage that is called pinch off voltage. So up to this voltage, what happens? After this voltage happens, we will see here. So the case 1, whenever we apply the VDS at the drain terminal, so this potential is more, the V is more compared to here. Here the V is less because with respect to distance, or we can call length. With respect to distance or length, the voltage will degrade. So that at the drain region, the width is, see here, it is more reverse biased. It is a more reverse biased and it is less reverse biased. If it is more reverse biased, the channel width is less, and here the channel width is more. More channel width, and here the less channel width. So this what we call as a wedge shape. The channel becomes wedge shaped. So due to wedge shaped channel, the current increases with respect to VDS. If VDS increases, the current IDS is also increases at this region. So the channel becomes like this, and like this. At a particular voltage, the channel cannot be increased. It will be pinched off. If you keep on decreasing the VDS, the channel becomes pinched off. It further the channel width doesn't change. Pinched off. So after this pinched off voltage, where the channel width is constant, that what we call as a pinched off, or this voltage what we call as a pinched off voltage, the current is constant. Okay, here when the transistor is on, there are two conditions. One is less than VDS. VDS is less than pinch off voltage, and VDS is greater than pinch off voltage. So what is a pinch off voltage or pinch off region? So the pinch off region is nothing but whenever we apply the VDS, the channel is not equally grown. The channel becomes a wedge shaped channel. The channel becomes wedge shaped because the potential varied with respect to the length of the channel. At the drain terminal, more potential is applied with respect to source terminal. So if you keep on increasing the VDS, the channel becomes more wedge shaped. Means that if you see the horizontal construction like this, so this is called wedge shaping. If you are increasing VDS, then it is more wedge shaping like this. So at a particular voltage, this will constant. This voltage where the width of the channel is constant, then that voltage what is called pinch off voltage. That is what we call as a VP. So whenever it reaches the VP, then the current is constant, because here the current is constant because the width is constant. Even the VDS increases. Even the VDS increases, it doesn't depend on it further. So this region, what we call where the current is constant, is called saturation region. Where the current increases with respect to VDS is called active region, or non-saturation, or ohmic region. This is what we call as ohmic region. Ohmic. Okay. So I hope understand there are three regions of the transistor. One is the cutoff, and second one is the active or ohmic region, and the third one is the saturation region. Okay, now we will see. I want to write the cases, different cases. So we'll see here. Okay, right. So these are characteristics, how it looks like. This is the characteristics, overall characteristics of JFET. This is the graph between VDS versus IDS, and this is the graph between VGS versus IDS. So here initially the current is maximum. With respect to increase in VGS, it will decrease. Here this is a ohmic region or non-saturation region, and this is what we call as a saturation region. We will see here there is a relation for the current, the output current. Already I told that there is a current flow in the JFET. The current flow in the JFET is ID equal to IDSS. IDSS stands for the maximum current at VGS equal to 0. The maximum current at VGS equal to 0 is called IDSS, where IDS we call as IDSS. This is the current at VGS equal to 0, the maximum current, what we can call, and it is into 1 minus VGS, get to source voltage by pinch off voltage whole square. This is the current equation for the current equation IDS for JFET. How to calculate? Okay, so where VGS is greater than, the condition is VGS should be greater than VP, and VDS should be greater than VGS minus VP. Okay, right. So we will see individually how the characteristics we will get. Okay, see this one. So coming to the first characteristics are called transfer characteristics, what we call as a transfer characteristics, because it is the relation between input voltage, gate to source voltage versus output current, drain to source current. So input versus output, that's why it is called transfer. Whenever there is a relation between input and output, that we call, the term is called trans. So these characteristics are called transfer characteristics. It is the graph between VGS and IDS. Already you know that the VGS is negative. So that's why we are taking the negative coordinate, negative x-axis, and the current is a positive, forward current. So the current is a forward current and the VGS is a negative. So we are using second coordinate. So this is a second coordinate system where the current decreases with respect to increase in voltage. Why it is decreasing? Because it is a PN junction. This is exponential graph, that's why. So when VGS equal to 0, this is the point at VGS equal to 0. So this current, what we call as IDSS, initially the current is maximum because the width is maximum. The channel width is maximum. So with increase in VGS, the width will degrade. Okay, whenever the width of the junction is decreases, the current is also decreases. So it is a PN junction diode. Already you know that for a PN junction, I equal to I naught into e power V by eta Vt minus 1. So it is exponentially decaying function. So the current is exponential graph, exponentially decaying graph. So at a particular voltage, these two are intersecting with each other, two junctions. So there is no channel. So the current will become 0. That's why the transfer characteristics at like this. So if you, while calculating these characteristics, the another voltage VDS should be constant. Assume that the VDS is equal to 1 volt. This is a graph. If VDS is increases to, if VDS is increases to 2 volts, for example, the VDS at 2 volts, then the current, the amplitude increases, the graph will look like the same. So the graph looks like same. So here the more current, because when VDS is more. So in order to draw the transfer characteristics, the output to drain to source voltage should be constant. This is the condition. It is the graph between VGS and IDS where the VDS is constant. VGS versus IDS. Okay, these characteristics are called transfer characteristics. This is how it looks like. So second one is the drain characteristics. So coming to the drain characteristics, this is depends on, it is a graph between drain to source voltage and drain to source current. So these are related to drain. That's why these characteristics are called drain characteristics. Or we can also call as output current and output voltage. These are also called as output characteristics. Okay, and already I told that up to pinch off voltage, after pinch off voltage, less than pinch off voltage and greater than pinch off voltage. Up to pinch off voltage, this is the, assume that this is the pinch off voltage, take one pinch off voltage. So whenever up to this level to this level, what happens? The channel, the width of the channels is wedge shaped and increasing, wedge shaped and increasing with respect to VDS. VDS increases, the width decreases, so the IDS increases. Where VDS is directly proportional to IDS. So the current increases with respect to voltage. But while drawing this VDS versus IDS, the VGS, the gate to source voltage, should be constant. So this is the maximum current what we obtained. This is the maximum current what we obtained when VGS equal 0, because the width is more. And after reaching the up to pinch off voltage, the VDS is directly proportional to IDS. So the graph looks like this one up to this region. After this one, when the second condition, case 3, VDS is greater than VP, the drain to source voltage is greater than VP. So then what happens? The channel width is constant. When the channel width is constant, the current is also constant, where width is not further increasing, constant. So the current is independent on the VDS. So this, where the current is constant, this region is called saturation region, and this region is called ohmic region. Why it is called ohmic region? Because VDS is directly, V is directly proportional to I. So this is our Ohm's law. So that's why it is ohmic region. In this ohmic region, this JFET is acting as a voltage variable resistor, VVR, voltage variable resistor. In the saturation region, it is acting as an amplifier. In the saturation region, this JFET is used as a amplifier. This is about the transfer and drain characteristics of JFET. So you need to remember 2 points. While getting the transfer characteristics, VDS is constant, VGS versus V. This is the graph between VGS versus IDS, where VDS is constant, and drain characteristics, the graph between VDS versus IDS, where the VGS is constant. Okay, so this is about drain and transfer characteristics of JFET. So finally, so it is a, already we discussed about, it is a voltage control current source, voltage control current source. The output current is controlled by input voltage. So output is current, the input is voltage. So then it is called conductance. So how to calculate this transconductance? So the transconductance can be calculated by the basic equation ID equal to, already we discussed, IDSS into 1 minus VGS by VP whole square. So we want dID by dVGS. Okay, so dID by dVGS. So we need to differentiate this with respect to VGS. We need to differentiate with respect to VGS. So GM is equal to minus 2 IDS by, we will get like this. This is the equation what we will go through. Okay, so this is about the summary of this one. Okay, so how this, so this is animation, how this JFET will work, how it is width shaped. Here, see this, at a particular voltage, the width further cannot be increased further. So this will, due to increase in VGS, the channel width will increase. This is how it's look like. So in this lecture, we discussed about the construction and operation of JFET and VA characteristics of JFET and the calculation of transconductance. Okay, so this is about the JFET operation. So this is the GM, how we will get. So this is the animation, how the animation looks like when with increase in VGS. If VGS is increases slowly, then the channel width is also decrease. The channel width is decreases with increase in VGS. That we have, that what we can observe here. Okay, I hope you got the key points. Today we completed that construction of JFET and operation of JFET and VA characteristics and transconductance, very, very important parameter. Okay, so thank you.
Vishnu Audio Visual Center, like and share and subscribe and click bell icon.